Let us talk about this problem. We are given a binary tree. We need to find out sum of nodes that are on same vertical line. Now when we say the nodes are at same vertical line, it means the horizontal distance of these nodes is same from the root. Let's define this term horizontal distance. Horizontal distance of root is said to be 0. Now when we go to a child, horizontal distance of that child is horizontal distance of this node minus 1. So horizontal distance of this node is minus 1 and this one is plus 1. For right child we add 1, for left child we subtract 1. For this node it's minus 2, for this node it's 0. So we have only one node at horizontal distance minus 2, that is why we have 5 first. Then we have only one node at horizontal distance minus 1, that is why we have 20. We have two nodes at horizontal distance 0. So our sum for this particular vertical line is 10 plus 15, 25. And we have only one node at horizontal distance plus 1, so we have 30. So we call it vertical sum because these nodes fall on the same vertical line if we consider horizontal distances as this way. That left has horizontal distance of its parent minus 1 and right has horizontal distance of its parent plus 1. Let's now see this example. Horizontal distance of this is 0, this is minus 1, this is minus 2, this is minus 3. And this one is minus 1, plus 1, 0, 0 plus 1, plus 1, plus 1 plus 1, plus 2. And this one is plus 1. So we have only one node at distance minus 3. Then we have only one node at distance minus 2. We have only one node at distance minus 1. And we have two nodes at distance 0. Then we have two nodes at distance 1. And we have one node at distance 2. So we sum all the vertical lines. We get the sum as 40, 35, 15, 20 plus 10, 30, 75 plus 25, 100 and 80. So that's the output expected for this input binary tree. Please note that if your tree becomes bigger, then it might not be possible to pictorially put all the nodes in the same vertical line. For example, if 25 also has a left child and that node also has a left child, then they'll cross each other, right? So the best way to figure out which nodes fall on the same vertical line is to use these horizontal distances. Simply mark the horizontal distances with every node and now sum all the nodes that are at same horizontal distance, right? So we use these values rather than drawing the vertical lines if we are given a big random tree. Now please pause this video and try to write down a program that takes a binary tree as an input and produces sum of all vertical lines or sum of all nodes at same horizontal distances one by one, starting from this leftmost to this rightmost. So the sums should be printed in the same order as they appear here. Let us now talk about the solution. The idea is to maintain a map. This map stores the sum for every horizontal distance. So if you see this tree, our map is going to have these many entries: minus 3, minus 2, minus 1, 0, 1 and 2. For minus 3, it's going to store the sum 40. For minus 2, it's going to store the sum 35 and then 15, then 30, then 100 and then 80. And once we build this map, our task is to simply traverse through the map and print the all values. And since we want to print these values from this leftmost vertical line to the rightmost vertical line, we want to use a tree map in Java or map in C++. Because map in C++ or tree map in Java, they maintain the items in sorted order. They are basically self-balancing binary search trees. So we should not be using an unordered map in C++ or a hash map in Java. We should be using a tree map, which is implemented using self-balancing binary search tree. So we have two tasks. First is to fill the entries in this map. The second is to traverse the map. Now the question arises, how do we fill entries in this map? Now you may pause this video again and try to think of a solution that takes a map, an empty map initially, and fills the map this way. We can fill this map using any of the traversals. We can use either in-order, pre-order, post-order traversal, or level order traversal. We just need to make sure when we are going to the left child, we decrease the horizontal distance by 1, and when we are going to the right child, we increase the horizontal distance by 1. So you may pause this video now again and try writing the whole function. Let us now talk about implementation of this approach. We mainly have two implementations here. One is Java implementation here and one is C++ implementation. Both the implementations are based on same idea. In both implementations, we have two functions. One function is our main wrapper function and other function is a recursive function. The wrapper function is this one, the bottom function. It creates a tree map in Java and map in C++. Please note that map in C++ and tree map in Java, they are internally self-balancing binary search trees and they maintain key value pairs, and the key value pairs are maintained in sorted order of keys. Smallest key comes first, then next key, right? So first we create a map. Now we call our recursive function that fills this map, right? This MP is filled by this recursive function, and after this map is filled by the recursive function, we are simply printing the content of this map. Values present in this map, not keys. So for this tree, we are going to get this output. Minus 30, 20, 40 plus 10, 50, and then 50. And the same thing we are doing here in C++ implementation. We first call the recursive function. After calling the recursive function, we simply traverse through the map and prints the individual values using sum.second. Now, let's talk about the recursive function. So this recursive function takes a map as a parameter. Let's now talk about this recursive function. This recursive function takes a tree map as an argument in Java and map as an argument in C++. And simply it does in-order traversal of the tree. And it does take one extra parameter, which is horizontal distance with respect to root. So initially we pass this horizontal distance as 0 when we call for the root. When root calls for its left subtree, it passes the horizontal distance minus 1. And when it calls for the right subtree, it calls plus 1. And every node does this thing. It reduces the horizontal distance by 1 when it makes a recursive call for the left side and increases the horizontal distance by 1 when it makes a recursive call for the right child. So in this implementation, we are making first recursive call for the left side, and then we are updating the value in map corresponding to the current node. So if we are here, we update the distance corresponding to 0. When we are here, we update the distance corresponding to minus 1. And how do we update this value? We first get the old value. If we do not have any old value, we consider the old value as 0. Otherwise, we get the old value. And once we get the old value, we add root.data to the old value and put it as new value for that horizontal distance. In Java, we need to write 2 lines of code. In C++, it's just 1 line. We can do map hd plus equal to root arrow data. In C++, if this key does not exist in the map already, then it will create a key and put the value as 0. And then it will add the root arrow data, right? So it works in 1 line in C++. So once we updated the value, we call recursively for the right child with hd plus 1. We are simply doing in-order traversal. And you can follow actually any traversal. You can do pre-order traversal, post-order traversal, level order traversal, because we are maintaining ordered by horizontal distances. And these horizontal distances have to be maintained whatever traversal you are using. Just make sure that you pass appropriate horizontal distance and do any traversal, and you will get the map created. And once your map is created, it's sorted by the horizontal distance, you will get the values sorted according to horizontal distance, and you will get the desired output. Let's see the working of this recursive in-order traversal. We called for root with horizontal distance is 0. We called for 20, left child with minus 1 distance, hd minus 1 we call for the left child. And then what we did was this left child called for its left child with horizontal distance minus 2. And when control came here, it began its execution from the first line. Root is not null. So what it did, it called for its left child is null and with horizontal distance minus 3. And after calling it for its left child, it updated its value in the map. So map of minus 2 did not exist earlier. It added this value 30 and made it 30. Now it calls for the right child. it was done with the map updation. Now it calls for the right child. In C++ code, it was here. Now it calls for the right child. And right child, it calls with -2 + 1 -1. But right child is null. After calling for the right child, this execution is over and it gives the control back to the caller. And caller now, which was waiting for left child to finish, left child is finished. So caller is going to now update its distance, its value with the horizontal distance corresponding to it. So horizontal distance of the parent is -1. -1 does not exist in the map. So it's going to create an entry with value 20. Now the parent is going to call for its right child and right child is 40. So 40 is going to make a call for null, left child of it, and then going to create an entry with 0 distance and value 40. Now the control comes back to the caller, right? Because these all calls are over, so the control comes back to the 10 call. And 10 call, when it goes to map 0 already exists with value 40. So it's going to take the old value 40 and it's going to add 10 to it, right? That's what we did here in these two lines. And Java automatically takes, and C++ automatically takes care of this here. So now caller adds 10 and makes it 50. Then it makes a recursive call for its right child, 50. And 50 again makes recursive call for the left child with +1 -1, which means 0. Then adds 50 to distance 1 and then makes a recursive call for the right child. So you can notice that we have built the required map in these recursive calls, right? We're getting the map built here. And after that, we are just traversing through the map in these two lines and these two lines in C++. We're simply traversing through the map and map is sorted. So it will print -3 value first and then -2, then -1 and then 0 and +1. So we get our required output. Now let's analyze the time complexity of this solution. There are two things that we do in this code. We build the tree map or map in C++ and then we traverse through the map. Now how many items can be there in this tree map or map? If HD is the total number of possible horizontal distances, for example, if horizontal distances are from -3 to 2, then we are going to have 6 possible horizontal distances. So if HD is total number of possible horizontal distances, then all the operations in this tree map are going to take big O of log HD time, because it's a self-balancing binary search tree, and if there are n items, they take big O of log n time. So we are going to do big O of log HD work for every node, and we have n nodes. So the time complexity is going to be big O of n log HD for the construction part. And for the traversal part, we just need to traverse HD nodes. This traversal of a tree map or map takes big O of n time when there are n items in this. Since there are big O of HD items, it's going to take big O of HD time. And HD is a lower term than n log HD. So we can say time complexity is big O of n log HD, where HD is total number of possible horizontal distances. So we have talked about the solution. We have talked about its time complexity. Now please try the next question, which is printing vertical order traversal of a binary tree. So when we say vertical order traversal, it means the nodes should be printed according to these horizontal values. But the trick here is, the important thing here is, the node that comes first in the vertical line should be printed first.